Hello! In this video, we are going to prove the following theorem. Let G be a group and H be a non-empty subset of G. Suppose for all A and B in H, A times the inverse of B is in H. Then H is a subgroup of G. Now, before we get into the proof, let's first remind ourselves of some things. First of all, what does it mean for G to be a group? It means that G is equipped with some binary operation and satisfies the following properties. So G is closed under the binary operation. The associative law holds. G has an identity element, and every element of G has an inverse. Now, to prove that H is a subgroup of G, we are going to be using the two-step subgroup test, which we have proven. And I'll leave the proof of that in the description below. So, the two-step subgroup test tells us, in order to prove H is a subgroup of G, all we have to do is verify the following two facts. We need to show that H is closed under the binary operation, and we need to show for all x in H, the inverse of x belongs to H. Now, the two-step subgroup test also tells us we need H to be non-empty, but we're given that, so we don't have to worry about that. And in proving this theorem, we are also going to be using the following preliminary result about groups. We have, for all group elements A is equal to the inverse of A. And to prove this, this is actually just a corollary of a result we proved in a previous video, which is, given any two group elements A and B, if A times B is equal to the identity, then this implies that A is equal to the inverse of B. So in particular, from the definition of inverse, we know that A times the inverse of A is equal to the identity. So then that means if we take A to be A and B to be the inverse of A, well then A is equal to the inverse of A. And that's exactly what we want. Okay, so now let's get into proving this theorem. To start out the proof, let's first give ourselves a group G with identity element E. Let's let H be a non-empty subset of G, and we'll suppose that this condition is true. The whole goal is to show that H is a subgroup of G. And to do that, we're going to apply the two-step subgroup test. And we're first going to verify condition 2. So to verify condition 2, since we're trying to prove a statement about every element of H, let's give ourselves an arbitrary element of H, called X. From here, the whole goal is to show that the inverse of X belongs to H. Now, applying our hypothesis, if we take A to be X and we take B to be X, well then A times the inverse of B is an element of H. In other words, X times the inverse of X is an element of H. But then, since X is an element of H and H is a subset of G, that tells us X is an element of G. But, according to this statement works for every element of G, so it must work for X. So we can conclude X times the inverse of X is equal to E. So this tells us that the identity belongs to H. So now that we know that the identity belongs to H, well now what we're going to do is, we're going to take A to be the identity, and we're going to take B to be X. If we do so, we again have that A times the inverse of B is an element of H. Or in other words, E times the inverse of X is an element of H. And remember, since X is an element of H, well again, X is an element of G. But remember, since X is an element of G, well that tells us the inverse of X belongs to G, right? That's the definition of the inverse of an element. So since the inverse of X belongs to G, well let's go to the definition of identity element. This statement works for every element of G, so in particular it must work for the inverse of X. So we must have that E times the inverse of X is equal to the inverse of x. So this tells us that the inverse of x belongs to H. And so putting this together, we see if x is an arbitrary element of H, well then it follows that the inverse of x belongs to H. So we have verified that condition 2 is true. Now we want to verify that condition 1 is true. Now, to prove condition 1, since we're trying to prove a statement about every two elements of H, let's give ourselves two arbitrary elements of H. I'll call them x and y. From here, the whole goal is to show that x times y belongs to H. Now, since we have proven that 2 is true, well, that tells us, since y is an element of H, we have that the inverse of y is an element of H. And now, applying our hypothesis, we're going to take A to be x, and we're going to take B to be the inverse of y. Well then again, we have that A times the inverse of B is an element of H. In other words, x times the inverse of y is an element of H. But by star, we know that the inverse of y is equal to y. So then we can substitute the inverse of y with y, so that tells us x times y is an element of H. And that is exactly what we wanted. So we have shown if x and y are any two elements of H, it follows that x times y is an element of H. So we have verified that condition 1 is true. So we have verified both of these conditions, so that's enough to say, by the two-step subgroup test, we have that H is a subgroup of G. And so this completes the proof. Now, this theorem is often called the one-step subgroup test. And so the way we proved it was we used the two-step subgroup test in order to prove the one-step subgroup test. Alternatively, you could actually use the one-step subgroup test to prove the two-step subgroup test. And you could give a proof of this, which is pretty similar to this one, which proves this without the two-step subgroup test. You're just verifying from the definition of a subgroup that this implies that H is a subgroup. And then you use the one-step subgroup test to prove the two-step subgroup test. The proof of the two-step subgroup test actually becomes really easy if you just use the one-step subgroup test to prove it. And so yeah, that's pretty much it for this video.